Welcome to Exploring Creation with Physical Science, 3rd edition, Module 7. We're on the second half of Physics Forces, and we're in the student notebook. Looks like this. And we are on page 195. We're going to start off with Newton's first law. We've got lots to cover today, so I'm going to be cruising. Feel free to pause at any point. I'll try to speak clearly and not too fast, but at the same time cover lots, okay? So we started out with, we covered this a little bit last time. We have a song for this. An object at rest tends to remain at rest, and an object in motion tends to continue moving in a straight line at a constant speed unless an outside force acts upon it. Newton's first law of motion. And then we have, it's also known as the law of inertia. Well, that doesn't fit in the song. Also known as the law of inertia. Well, okay, we can make it work. All right, so what do we have? Some notes, some ideas from the text on what are some laws of inertia examples. So soccer ball will just sit there on the ground until a kick moves it. And then the friction is what slows it down. Friction from the grass or the ground eventually slows it down. Otherwise, it could theoretically keep going forever, but nothing's perfectly smooth, right? So we always have that friction. All right, here's an example. You and the car are going the same velocity. When the brakes are applied to the tires, it slows or stops the car, but you are still moving at the same velocity. It's the belt, your seat belt, that slows you down. So here's this person going along on the road, and then somebody plays the brakes, that what stops them is the seatbelt, right? And so because otherwise they were going the same, the car is going say 50 miles an hour, the person's moving at 50 miles an hour, the brakes are applied to the car but not to the person. So we need something like the seatbelt to stop the person. I like this book. It's got all sorts of good reasons why we should wear seatbelts and not play on railroad tracks and all sorts of stuff. All right, Cowboy's riding his horse at a fast gallop. Suddenly, the horse plants his feet and stops. As a result, the cowboy falls off his horse. Will the cowboy fall forward, backward, or the left or the right? And I circled forward. That's because if he was moving forward, and then all of a sudden the horse stops, the person has not stopped, right? So they go forward. All right. Cars traveling down the road at 30 miles per hour. A truck driven by a reckless driver comes up from behind with a speed of 50 miles per hour, and the truck slams into the back of the car. It doesn't say that like either one of them stops. It just kind of like keeps the speed up from the back of the other car. Will the car's passengers be flung forward or backward? And so it's the answer is that the truck will push them faster. So they'll be flung backward, like you would be when you're going down a roller coaster or something. You go backward until the back of their seats forces them to the same speed as the car. So there's always a force making movement happen, correcting movement, things like that. All right, a plane is dispatched to drop supplies to stranded hikers. Hikers marked an X on the ground. Boop, there it is. And here's where they could drop this cargo from. If they want the cargo to land here, do they want to release it from the plane at this point, or this point? You'd think it'd go straight down, right? But that cargo is moving this direction, we'll call that eastbound, with the plane. So that motion, it will only have, the cargo will only have gravity as a force on it, right? Otherwise, it's got the velocity already still going. And so it will continue to go forward. So we need to drop it from point A, because because it'll continue to move on it and it'll fall. All right, so there's multiple forces on that. I should, instead of only gravity, because it's still got the inertia of the plane, right? It wants to keep moving, so don't stop me. Don't stop me now. All right, here we go. Newton's second law. Force equals mass times acceleration. Newton's second law, Newton's second law. Force equals mass times acceleration. And that's what's on the rest of the page too. So there's lots of that. We did this before with the arrows. And I think it's pretty simple. We can just take the arrows and add them or subtract them from each other. In this situation, the total force would be the movement from the man, the force from the man, and the force from friction. And in this situation, it doesn't actually give us an exact amount, so we can't say, we can only guesstimate that he's pushing harder by a little bit than the friction from the tires. So he's going to get forward movement from that. So, and on this one, we have a little dog helping. You see the dog? And that doggy force is actually helping the man enough to actually make the movement happen even faster. So here's our illustration of, we have a little bit of movement, but then here, when you add the force from the dog and the man together, and so just subtract the friction from the tires, we have even more movement. So good job, doggy. Good job. You did good. All right. So here we are, page 199. And a man pushes a broken car to a gas station. Ignoring friction, what force is needed to get to 0.03 meters per second squared east? So here's what we know. We know we have a mass of 1,500 kilograms. Acceleration, it tells us in the story, is this amount eastbound. And what is the force in newtons? And newtons are this, kilograms per meter second squared, so no conversions are needed. So that's important that we already know that. All right, so what equation are we going to use? Newton's second law, Newton's second law. Force equals mass times acceleration. And we're going to plug it in right there. Mass times acceleration. And here's our answer. We've got 45 kilograms per meter and times meters over second squared, which is a newton. Okay, so we got 45 newtons to the east. Yay! So we did that one. Page 200, a car accelerates at a green light. What is its acceleration? So my kids don't know they're on my recording. It's funny. I did tell them I did. Mass equals 1,000 kilograms. Force equals 4,000 newtons. What is the acceleration in meters per second squared? Well, this one we don't have, we're not looking for the F here. We're looking for A, so we need to rearrange this. And this is how you do that. If you divide this side to get the A, or to get the M, we have to, well, how do you do that? You divide them both. But if you have to do division on this side, you do division on this side. So that's how we get that. So, all right, so here we are. We're going to plug it in to this right here. We have acceleration equals 4,000 divided by 1,000. And we're going to be able to eliminate some of those kilograms right there because we've got it on both sides. We're going to go straight across. We have 4 meters per second squared. So we just take that one out from under it, and it's a whole number 4. So we have 4 meters per second squared forward. So that's its acceleration. We figured it out. All right, a rock is pushed and accelerates at 0.12 meters per second squared. The rock happens to be 300 kilograms. If 400 newtons is applied, what is the frictional force? Okay, so here is what we know. We've got the mass, acceleration, and we got the force of the worker who's pushing the rock. And here we go. So what is the force in newtons, and what is the force of friction in newtons? So we got two questions there. So for first off, we have force equals mass times acceleration. And so let's figure this out. We've got 300, here's our mass, times acceleration, divided out. We've got 36 newtons. So and then we need to move over here. We're on page 201. We've got mass, still 300. The acceleration is still 0.12 meters per second squared. We still know the force of the worker has not changed, but now we know I believe this is the net force. It's the overall force. So how can you do that if you don't know what the frictional force is, though? We are looking for, that's just the force of the worker. Is that right? No, that's the worker here. My goodness. What is this? Is this the net force? Let's figure it out. Let's see what we can figure, because we've got, it's the actual movement. That's what this is. Because if you look at it here, we've got force equals, this is defining it for us, the worker's push minus the frictional force. So what this is the actual movement, okay? But right now we want to know, what is the frictional force? So frictional force equals, we flip it around, and if we, this situation, we would just do the force of the worker minus overall force. So we plug it in, and we get 364 newtons southbound. Because friction always opposes motion, the rock was being pushed north. But because it was frictional force, it gets the south direction. Okay? It's resisting that northerly push. All right, new question. They have lots of questions in this section, so it makes it a little extra long, but we'll get through it together. So a man pushes a desk, 100 kilogram desk. It doesn't sound very heavy. Because kilograms are little. The static frictional force is 196 newtons. The kinetic frictional force is 110 newtons. How much force is necessary to get it moving? Well, if the desk moves at 1 meter per second west, how much force was used? Wow. I think I was getting really sleepy there when I was doing that. My handwriting was really disintegrating. Okay, so here we go. This is what we know. Mass was 100 kilograms. We got all this written down. We're looking for the force from the man pushing the desk. That's all we're looking for. We've got static frictional force and kinetic frictional force already in here. We know that that force equals mass times acceleration. Thanks to Newton. So let's plug it in. We've got force equals 100 kilograms times 1 meter equals 100 newtons. So then we have part B. We need to do a little bit of more math here because we're looking for the force of the man. Here's how we determine that the force is the push of the man minus the kinetic friction. So we flip it around and we add the man's force to both sides, and we go. And so here we go. We've got force plus kinetic friction. Plug that in using those numbers up there. Sorry. We've got the force number there. This is our kinetic friction. and we add them together, and it's 210 newtons to the west. Okay, so that's how we figured that one out. And now we got an on your own question. Man, they're really making us work hard this time, but this one's not too bad. A box that is 15 kilograms is given an initial shove, push, and then allowed to slide across the floor. No person pushing it. If the box slides north and experiences, I circled that so you remember which way it's going. Box slides north and experiences an acceleration of 1.1 meters per second to the south. What is the kinetic friction force between the box and the floor? All right, so we've got our mass, we've got our acceleration. What is the kinetic friction force? Frictional force. Kinetic frictional force is simply mass times acceleration. And we've busted out, and it is 16.5 newtons to the south, because the frictional force always goes the opposite direction, as we did before. So I thought there's all this like flip-flop thing going on, but in this one, evidently not. So I will not try to explain that one any more than I just did. All right. 7.9. Suppose someone wanted to keep the box in problem sum point 8 moving at a constant velocity. What force must be applied in order to accomplish this feat? Well, we already knew that the box was 15 kilograms. Constant velocity means there's no acceleration, so we have 0 for acceleration, and we're looking for the force. So we busted out. First, we start out with finding out the force. Then we use the next, which is net force, Fn, equals applied force minus frictional force. This is kinetic frictional force. It's just a tongue twister. All right, so we're looking for this. So we're going to flippity-floppity things around so we can get the applied force. And this is our new equation, because this helps us determine the question mark is now over here. And we plug in the data that we have, which would be the 0 force plus the 16.5 kinetic frictional force. And we know this was south, and so the 16.5 newtons northbound is because the box was actually moving northbound in 7.8. As you recall, I circled that. So, all right. So in this story, a kid wants to move a block, all right, and it's it's got a force of 30 newtons west, but is resisting motion that much. It's capable of static friction, as the static frictional force is 30 newtons west. Kinetic frictional force is 20 newtons west. What force must the child exert in order to get the block moving? Well, it moves 1 point. They give you all this information, but it really only needs to overcome static friction. So we really just need to exert a force slightly more than 30 newtons east. So it's a little bit of a trick question, because they give you all this data that you don't use, and it ends up making you think that you need to do all sorts of formulas, and in this one it's just noting that the thing that needs to be overcome is the static friction. So just push harder, kid. You got this. All right, so we're on week 15, day 3 here, page 205. Weight and mass. The mass is the amount of an object or a measure of an object's inertia. More mass means the more it will resist change in motion. Weight is the force of gravity acting on an object. So that's what the difference is between mass and weight. what is the equation? Weight equals mass times acceleration due to gravity. All right, so an astronaut is 121 kilograms. They said, what is his weight on Earth? And just to be ornery, I would change the astronaut to a female. And so I said, what is her weight on Earth? So here we go. We've got, this is how much she weighs on this is how much she weighs on the moon. That's what it said in the book, I believe. The gravity is 9.8 meters per second squared. What is the weight in newtons? So this is the weird thing. We don't weigh ourselves in newtons here on Earth. So this is our formula. Weight equals mass times the gravity. Acceleration due to gravity. So that's what that was really about. So the answer is, we plug everything in, is 1,185.8 newtons. Well, what would her weight be on the moon? On the moon, we have to figure out first what we know. And so hold on a second. So so they're asking about newtons. I'm sorry. So I got mixed up. So this first initial thing was not saying that she was on the moon. This is how much she weighs on the moon. This is just how much she weighs. What is her weight on Earth? I would just take that many kilograms and convert it to pounds. But they wanted to know in newtons. So because we're learning physics. All right. So what is her weight on the moon? This is her acceleration due to gravity. And this is the new information we've been given here, 1.625 meters per second squared. And we're looking for weight. This is our handy-dandy formula. And we're going to plug it in, and we get 196.6 newtons. The astronaut's mass is the same on Earth and on the moon, but her weight is different. You can tell she's a lot heavier here on Earth due to gravity than she is on the moon. All right? All right, we are on Newton's third law of motion, page 207. This one has a fun song. It goes, an equal and opposite reaction, Newton's third law. All right, I won't keep going on that. Don't worry. You're welcome. I stopped. What is an example? Well, I drew my example. It's a ball being thrown and bounced. So that's what I've got there. This action has a equal reaction. All right. On your own, it's asking us if a player hits a ball with a racket. How do we know that? It asks what evidence do you have that the racket exerted a force on the ball? What applied the equal and opposite reaction? What evidence do you have for this force? Well, the strings on the racket bow, and the racket, racket bow. I can't say that. They went like that instead of just staying like that. They when it hit. So they bow, and that means because there is an equal and opposite reaction, we have evidence that a force was applied and happened between the ball and the racket. So on our own 7.12, an ice skater stands on the ice and skates. He's holding a ball. Assuming that friction is so small it can be ignored, what will happen to the skater if he suddenly throws the ball hard to the west? Well, it should move the skater to the east because not having any friction. And so evidently, every time we throw a ball, we should move the opposite direction that we threw the ball or threw anything, except that frictional forces stop us. Isn't that fascinating? Like, what? force. All right, so got some pictures here. Finally, something interesting. Electromagnetic force is the force. There's like, we're looking at 4 fundamental forces. Okay, this is the first one. Electromagnetic force. This is the only force that can attract or repulse. I want to say repel. That's why it's messy there. It's like repel. No, attract or repulse. Those are the words that they used. So we'll stick with it. It's between particles with an electrical charge. Light bulbs have electromagnetic waves. This is the second strongest force. This is when they attract each other. You have a positive and negative. They'll attract each other, and that's also known as like static electricity. This is called electric force or magnetic force, but it's electromagnetic force. It's got all of it in it, right? When they repulse, or we have a negative and a negative, or a positive and a positive. These are like magnet diagrams here. The positives and the negatives, boing, they repel each other. I want to say repel, but it's probably repulse. They just think, you are disgusting. Get away from me. I don't like that. So that is what happens right there. Strong force is your next one up. All right. This is a nuclear force. Is the only, they only have attraction because force is so strong, it overcomes the force of repulsion. Okay. And it has a very short distance. So that is a nuclear force. All right. And we have the weak force. The weak force is less powerful than the strong force. It also has a short distance. Its uniqueness is that it plays a big role in particles breaking down or decaying, governing certain radioactive processes in atoms, where one type of quark changes into another type of quark, which can cause a proton to turn into a neutron or vice versa. And this changes elements from one to another, which is crazy. So this is important in nuclear fusion. It powers the sun and hydrogen bomb, which I'm sure does not look like a cartoon bomb. But weak force isn't that shabby because it does do some mighty things. So you can just imagine how strong the strong force is if that is the strongest force, and this is what the weak force does. And later on it mentions that the strong force is what holds nucleus together in our atoms. And so now you know why atoms are so amazingly powerful. All right, one more. Gravitational force. It is the weakest of the forces, but it's a big mystery. 2 big theories on it. I thought we're down here, but no, they're right here. They're quantum gravity, like quantum mechanics. They believe that gravitons are responsible for gravity. And the second theory is Einstein's general theory of relativity, which is down below. We'll get to in just a second. But first we're going to look at what we do know for sure about gravitational force. Thank you, Mr. Newton, again, Isaac. We know that every object in the universe attracts every other object. It's why don't 2 pens on a table creep nearer and nearer to each other? Because frictional force is stronger. So it is the weakest of all of the forces. Gravity is. So, yeah, isn't that fascinating? I'm learning so much. All right, what is Einstein's general theory of relativity state? This is the big the theory. Okay, so one of the 2 big theories. Space bends in the presence of an object with mass, and so does time. Space and time bends in the presence of an object with mass. I just think there's so much to think about with that. Like, I think here on Earth too, like when I walk into a room, do I bend the space and time? All right, here's a picture Here's a picture of the Earth on a curved path. Oh, so Earth is going around the giant sun there, right? And the sun is much heavier. And so the Earth actually follows the curve of space that is made from the mass of the sun. Isn't that fascinating? I'm just blown away by all this. Okay, 2 more questions and we're done. Can you believe it? All right, which universal force can repel as well as attract? Well, that was the electromagnetic force. And which universal force acts to hold the nucleus together? That was the strong nuclear force. All right, good work today. And we'll see you next time. Bye-bye.